Hello students. So in the previous session, we saw what do you mean by clustering? What are clusters? We also saw the different applications of clustering, as well as what do you mean by a hard cluster and a soft cluster. Now, in this video session, we are going to study one of the algorithms that are used for unsupervised machine learning technique, which is called as expectation maximization algorithm, or sometimes referred to as EM algorithm. So in today's session, we will cover the problem of latent variables for maximum likelihood estimation. What is EM algorithm, that is expectation maximization algorithm in machine learning? How does this algorithm work? Applications of EM algorithm, followed by advantages and disadvantages of EM algorithm. Firstly, let us study what is the problem of latent variables or missing variables for maximum likelihood estimation. In statistical modeling, one of the most common problem that arises is how an individual can estimate the joint probability distribution for a given data set. So you have got a data set, and from that particular data set, you have to estimate or determine the joint probability distribution. This is the most common problem. So if I'm considering a data set and trying to plot a particular graph of it, so the problem of latent variables for maximum likelihood is basically nothing but how do I get a joint probability distribution? Okay, so basically we want our curve to be like this, joint probability distribution. All right. So now let's see what is probability density estimation. Okay, so we will find out what are these latent variables and how we can solve this problem of latent variables. Okay, so what is probability density estimation? Probability density estimation is fundamentally the construction of an estimate, okay, a prediction based on observed data. All right, so the prediction is performed or estimation is performed on the basis of observed data. It basically involves selecting PDF, probability distribution function, and the parameters of that PDF that best explain the joint probability of the observed data. Let me simplify this for you. Basically, what it is trying to say is we are going to plot all the observed data on the x-axis. Okay, and the probability density function will be specified here on the y-axis. So we are nothing doing but constructing the estimate on the basis of your observed data with respect to the density function. And from there, we are trying to identify what are the parameters of that particular density function that best explain the joint probability distribution. All right, because we are interested in finding the joint probability distribution. As you can see, we are having two curves over here for joint probability distribution. So we are interested what are those parameters of that probability density distribution function that helps us in identifying the joint probability of the observed data. So the first step, how do we do this? Is nothing but create a plot. Plot is nothing but a graph of observations in the random sample. As I showed you, you will first create the plot. So this is the code where I am plotting the random sample. I have basically imported the libraries, that is matplotlib.pyplot as PLT, and from NumPy I am importing. I am using basically the package random, and from there I am importing normal. Now I need to plot a random sample. So what I have done, with the help of the normal function, I am keeping the size of that sample to be 2000 and plotting the histogram using the matplotlib library, where I am keeping the observations or the number of observed data to be 50. So the choice of the number of bins plays an important role here in terms of the number of bars in the distribution and in terms of how it is densely populated. Let us look at the histogram. So what it is done over here, I have just taken a random plot having size 2000 and plotted a histogram where I have kept the bin value to be 50. Alright. Now, I am simply reducing the bin value from 50 to 5. So now what has happened? The distribution is divided into 5 bins. So what do you observe? Now instead of having 50 distribution, you have got over here as 5 bins. So what does this imply? The density estimation requires selecting a probability distribution function. Distribution over here is nothing but bins, and the parameters of that distribution that best explains the joint probability distribution of the sample, the random sample which I had taken of sample size 2000. So density estimation requires probability distribution function, that is bin size. I kept it initially to 50, then I changed it to your 5, and the parameters of that distribution that best explain the joint probability distribution of the sample. Now what are the problems with this density estimation? You must be wondering, how do you actually choose the probability distribution function, that is the bin value, and how do you choose the parameters for that probability distribution function? So these are the problems of your latent variables. If you recollect, I mentioned this initially. Okay. So one of the most common technique of solving this problem is MLE, maximum likelihood estimation. So in statistics, maximum likelihood estimation is the method of estimating the parameters, okay, predicting or guesstimating the parameters of a probability distribution by maximizing the likelihood function. Okay, that is by maximizing the probability function in order to make the observed data most probable for the statistical model. I repeat, maximum likelihood estimation is a method of estimating, predicting or guesstimating what are the parameters of a probability distribution by maximizing the likelihood function. You have to maximize the probability function so that the observed data is most likely or most probable for the statistical model. But there are some limitations. of MLE, that is maximum likelihood estimation, it does not really mandate or make it compulsory the model to have access to all the data inside. And it assumes that the variables relevant to the model are already present. But in some cases, some relevant variables may remain hidden. Not all the variables may be seen. Some variables may be hidden. And these hidden variables may cause inconsistencies. And these observed or hidden variables are nothing called as latent variables. So MLE has got a drawback that it does not have access to all the data inside. If some variables are hidden, then they remain hidden and it could result in inconsistencies of our results. So those hidden unobserved variables are nothing but called as latent variables. So in the presence of latent variables, a conventional maximum likelihood estimator may not work as expected, and one such approach of determining appropriate parameters in the presence of latent variables is EM algorithm, expectation maximization algorithm. So we have got, in summary, I would like to say that the problem of latent variables which exist that cannot be solved by MLE, maximum likelihood estimation, is solved with your EM algorithm, expectation maximization algorithm. Now let us see what is this algorithm all about. So EM algorithm in machine learning, it was proposed in 1977 by Arthur Dempster, Nan Laird and Donald Rubin. It is basically used to determine the local maximum likelihood parameters of a statistical model in case the latent variable is present or the data is missing or incomplete. So it considers all the conditions. If the latent variable is present or it is missing or the data is incomplete, what MLE cannot do, maximum likelihood estimation cannot do or cannot solve the problem of latent variables, that is being solved by your expectation maximization algorithm. Let us see the definition. EM algorithm is an iterative estimation algorithm. The keyword iterative is very important. It is an iterative estimation algorithm that can derive the maximum likelihood estimates, that is nothing but MLE, in the presence of missing or hidden data or incomplete data, that is nothing but in the presence of your latent variables. So there are four major steps in EM algorithm. The first step is you have to consider a set of starting parameters in the incomplete data, sometimes called as observed data. So you have got a data which is incomplete or observed. From that data, you will be assuming a set of certain starting parameters. And we assume the observed data comes from a specific model. This is nothing but our initial hypothesis. Make a note of it. Assume observed data comes from a specific model. This is the assumption or the initial hypothesis that is considered in expectation maximization algorithm. The second step is called as expectation step or E step. Now using this observed or incomplete data that is available to us, we estimate or guess the values of the missing data. Okay. So with the available data, we start performing estimation, okay, of the missing data. The third step is maximization step or M step. Complete data generated after the expectation step is used in order to update the parameters. So basically what is done over here is we will be performing step number 2 and 3 completely until the convergence is met. That means which missing data we were looking for, that missing data is obtained. Once that is done, convergence is met, then only we terminate out from the expectation maximization algorithm. Till then, we keep on performing step number 2 and 3. That is, from the observed incomplete data, we perform the guesstimation of the value of the missing data. At the same time, we perform the maximization step only after expectation step is used in order to update the parameters. And the algorithm comes to a halt only when convergence is met. Just a graphical illustration. We have got a jigsaw puzzle and here the data is missing. Alright, so the first step, we are assuming that the data is coming from a specific model, that is our initial hypothesis. And now we are basically trying to fit this particular jigsaw puzzle, which is your E step or expectation step. And here we will keep on performing until and unless we obtain the actual value for this particular missing jigsaw puzzle. Once the value is obtained, then we terminate. Till that time, the algorithm will be switching between step number 2 and 3, that is expectation and maximization step. This is the flowchart of EM algorithm. We start our initial values, that is from incomplete or observed data. We consider a set of initial values, which is nothing but our initial hypothesis. Then that is given to the expectation step, where we basically try to find out the missing value. And from there, we give it to the maximization step. Maximization step checks whether the missing value which is there is appropriate or not. If the convergence is met, we terminate, else an iterative loop is carried out or conducted in EM algorithm. Uses or applications of EM algorithm. It can be used to fill the missing data in a sample or a data set. It can be used as a basis or foundation of unsupervised learning. So in clustering, we can use EM algorithm. It can be used for the purpose of estimating the parameters of HMM, that is hidden Markov model. We have seen HMM. We can use this model to estimate the parameters, that is transition probabilities can be found out, or your estimation probabilities can be found out with the help of expectation maximization algorithm. It can be used for discovering the values of latent variables. As I told you, latent variables or hidden variables which MLE, that is maximum likelihood estimation, cannot identify, that can be discovered using expectation maximization algorithm. Advantages: it is always guaranteed that likelihood will increase with each iteration. So every time we find out a new value of the missing data, the probability increases. The E step and M step are often pretty easy for many problems in terms of implementation. Solution to M steps often exist in closed form. Disadvantages: convergence is slow. It takes a lot of time. It makes convergence to the local optima only. We don't reach the global optima. Local optima can include local maximum and local minimum, but we are interested in global maximum and global minimum. So convergence is met to the local optima only. It requires both forward and backward probabilities, but in numerical optimizations, in numericals, we consider only forward probability. Thank you.